So far in Engineering Mathematics 5 we have done second order differential equations and partial differentiation. Now we move on to the third outcome of Engineering Maths 5, and that is Laplace transforms. Now, as I've said to you before, I think Laplace transforms are probably the most difficult thing that we do throughout the HND engineering course. So as long as you follow the steps and you remember your knowledge of partial fractions and normal algebra, we should be alright. Okay, so let's have a look at what they do for us. Now, the most important thing in engineering that controls so many different things are differential equations. So we've seen them in first order and second order, so they look something like this. So it can either be dy by dt or dy by dx. Something like that, for example. Right, now normally, or using what we've done so far, we would use techniques to solve them using both involved with integration and differentiation. Right, now what we can do with a differential equation, now after I've integrated it we get a solution to this bit, so it's just y equals something. Right, that's what we've done in the first outcome, second order differential equations, and what we did in the last outcome of Engineering Mathematics 5. Now, if we do Laplace transform, right, to our equation, now we'll show you how to do that later, we end up with a normal equation with the variable s instead of t, or s instead of x, and then we can do partial fractions or just use normal algebra techniques. So that's partial fractions normally, partial fractions, algebraic long division, simultaneous equations, any of that kind of stuff that we've done in maths before. And then all we need to do is do an inverse Laplace transform, and it takes us back to the answer, the solution y equals. Now, you might say, well, why do I have to bother with doing something over 3 steps when most of the time, or most of the time I can do it over 1 step? It's not always possible to integrate and differentiate the variables in a differential equation. Right, the differential equations that I've showed you so far have all been nice functions. So if your function is not nice, there might be a discontinuity in it, then we have to use Laplace transforms, then normal techniques, then inverse Laplace transforms, right? Because we saw even when we did integration by parts, there was some integrals that we couldn't do. Right, now the next bit is just going to show you how you get to, or how the book gets to what a Laplace transform is. But as far as you're aware in engineering, all you need to do is to be able to use a table of standard Laplace transforms. So you've got to be able to apply it. You don't need to be able to prove how you got to the Laplace transform. Right, so the Laplace transform the function, and we tend to use t because we tend to use the time variable in differential equations. I know we've used x before, but it tends to be t. Is given by, so if you've got f of t, and you do the Laplace transform to it, it's a capital L, so that means the Laplace transform, curly brackets, f of t. And the formula for that is it's the integral between 0 and infinity of e to the power of negative st multiplied by f of t dt. So the Laplace transform of your function is you integrate the function between 0 and infinity whilst at the same time multiplying it by e to the power of negative st. Right? So you multiply by e to the power of negative st first, then you need to find the integral of the whole thing. Right now, a couple of things you've got to remember is infinity is not a real number, it's a concept, so when we do integrate something towards infinity, we need to use that limit notation. Right? So, I'm just going to do one example of how that works, but as I said, the rest of the time we're just going to use the table. Right, so this is finding the Laplace transform of f of t equals c. Right, now remember, if we're using the letter c, that just means it's a constant. So that means it's 4 or 7 or negative 100 or whatever. But I'm just going to do it for the general case c, so that means we can apply it to any number value at all. Right, so this is from first principles. Which is this here. Right, so we know that the Laplace transform of f of t is the integral between 0 and infinity e to the power of negative st f of t dt. So our function f of t is c. So the Laplace transform of c is the integral between 0 and infinity of e to the power of negative st c dt. Now, what we always do is mathematical notation to keep things the way we like to write them. I'm just going to move that over. I know it gets a little bit blurry over this side. The camera's not the best in the world. So what we tend to do is we always write the constant first. So if that was e to the power of negative st times 4, we'd write that as 4e to the power of negative st. So I'm going to put that c at the front, like just like we would like that. Right, now in engineering 3, we looked at the fact that you shouldn't have infinity as a limit. So what you should do is we're going to change that limit to the letter b, 0. This is all notation. It doesn't really matter. If you put in infinity directly into an integral, you lose a mark because it's bad form. It's not correct mathematics, because infinity, as I said, isn't a real, it's just a concept. It's not a clearly defined number. So to get around that, we always swap infinity for b, and then we just write this limit as b goes to infinity. That means the limit as b goes to infinity. And that takes away the fact that we've got infinity in a limit. Instead of having infinity in a limit, we've got this letter b. And all it does is it allows us to make a judgment call later on. Okay, so I'll just leave that up there. So I'm going to leave that limit as b goes to infinity, and I'm just going to leave it as and I'm just going to integrate it. So nothing happens with that until we've integrated it and we've substituted in our two limits. So the Laplace transform of c equals the limit as b goes to infinity. Now remember, it's definite integration, it's got limits, so that means it becomes a square bracket, and the limits move over to the other side to show you that you have actually integrated it. Right, now if I integrate this, well, the standard integral tells you, well, that's just a number. I'm integrating t, so if it was differentiating, the number in front of the t would come and multiply it, but when we're integrating it, whatever's in front of the t goes underneath and divides it. So that's c e to the power of negative st divided by negative s. That's a standard integral. Right, so let's substitute in my limits. Remember, make your brackets curly brackets there if you can. So that means it's the limit as b goes to infinity of, and remember, it becomes curly brackets. So that's c e to the power of negative s b over negative s. Now remember, we're differentiating with respect to t, so that's where the limit goes in. And remember, let's take away, subtract ce power of negative s times 0 over negative s, like that. So it's top limit substituted in place of t, and the bottom limit substituted in place of t. Right, so all I'm just going to do is kind of simplify this down. I should never be dividing by a negative, so I'm just going to bring that up and make the whole fraction negative. So that's negative ce to the power of negative sb over s. Take away, again I'm going to bring that negative up. Now remember, anything to the power of 0 is 1, so that whole thing, e to the power of negative s times 0 is 1, so that's c times 1. So that gives me that there. E to the power of 0 is 1. Right, so I've noticed there that that becomes a plus. So I've got that there. And hopefully you're relatively happy with where that's come from and just integrated something as normal. As you will be aware later on, the s's and 5's end up looking the same and they end up getting complicated, and loads of examples in Laplace transforms involve 5. So if there's a 5 in the question, you've got to try and get your 5's and your s's look different, but anyway, I've not got that problem just now. So what I need to know is what happens to this term here. Right? So what I can spot is it's a common factor of C over S in both terms. Right, because that's got C over S in it, and that's got C over S in it. So that's a common factor. You don't necessarily need to take that out now. So what I was saying is, I need to know what happens to this bit here. Right, so as b goes to infinity, I need to know what happens to the term that's got the b in it. Right, so if that b becomes a really, really, really big number, what's my answer? So I just get my calculator. So shift E -5 times typed it all in, so you just put in a really big number and it tells me that as b becomes a really big number, and I just made up something at random, just type it into your calculator, that tells me that this thing becomes 0. So that means that I've dealt with my limit as b goes to infinity, and I've dealt with the b from inside, because these comes up here. So that gives me c over s, that is 0, the Laplace transform of c, just c over s. Okay, and all that means is, so if you've got the Laplace transform of the number 4, that would just be 4 over s. So I was just dealing with if c is any number. Laplace transform of -40 is -40 over s. Okay, so all I was proving is if you take the Laplace transform of a constant, it just gives you that constant over s, and s is our variable. Right, now the exact same thing can be done for all other terms, right? So what we say is now, if f of t equals c, which is a number, constant, then f of s, if it's a capital, that means it's the Laplace transform. The other thing that gives it away is the fact that they've changed the letter from t to s. So they're going from t space to s space. And a normal function becomes a Laplace function because it becomes a capital, right? As c over s. Right, and as I said, right, so thankfully you do not need to find Laplace transforms from first principles in this course. They are on page 18 of our Laplace transforms booklet. So our Laplace transforms booklet looks like this, and it's up in the files part of Microsoft Teams. I will, when there's a worksheet or whatever, try and show you the worksheet so that you don't necessarily have to download it if your Microsoft Word or whatever isn't working in your computer. But do your best to try and download a copy that you can open. Right, so page 18. Is our magic table. Right, so this is what you need for any question involving Laplace transforms. This will be given to you in the exam and should be given to you in pretty much any exam you do involving engineering and Laplace. Right, not always. If you go to some unis you have to memorise them, but in the modern day, if you're using Laplace transforms, you'd probably just Google it anyway, so I think it's probably right that we give you them. Right, again the camera's going to be a bit fuzzy, but hey. Right, so just as we worked out, if you have a constant, a number, so 5, 6, 7, whatever, the Laplace transform of that is that number over S. Right, if you got to find the Laplace transform of t, that's just 1 over S squared. If you want to find the Laplace transform of t to any other power, it's that power's factorial over s to the power of that power plus 1. So if it was t cubed, it would be 3 factorial over s to the power of 4, because you add 1 on. Right, now, a really important part of our Laplace transforms is exponentials. If you've got e to the power of kt, it just becomes 1 over s take away k, so whatever number's in the coefficient or the number in front of t. Sine, you've got 1. Cos, you've got 1. Please be careful with these because there's a different one for if there's a t in front of your sine, and a different one if there's a t in front of your cos. Right, this bit here tells me that if there's a constant in front of your function, your Laplace transform, like a 4, then the constant just goes in front of the Laplace transform. So this is exactly what you think. So if I had 4t, that's 4 times t, so the Laplace transform is 1 over s squared, so the Laplace transform of 4t would be 4 over s squared. But I'll do a few examples of that. Right, now then the biggies and important ones for us, the first derivative. If you're taking the Laplace transform of the first derivative, we get this function here. If we take the Laplace transform of the second derivative, we get this expression here. This here is called the Dirac delta function. We'll come to that right at the very end. And this here is the second shift theorem, and again we'll come back to that a lot later on. Right, and if you can see at the bottom of the book, it says included are Laplace transform for derivatives, so those two there, and the Dirac delta function, which is that there. It says these are useful for the solution of differential equations and will be considered in the coming sections. So we will see a lot more from that over the course of this outcome. Right, so I'm going to keep my Laplace transforms booklet by my side. You see it? It's just here. So that's what I'd expect you guys to do when you're doing any questions on involving Laplace transforms. Right, try and get a printout of it. If you can't get a printout of it, try and keep it up on your phone or keep it up on your tablet or whatever you're doing whilst you're trying to do these questions. I know it's quite annoying, but we have to suffice in these difficult times. Right, so finding Laplace transforms using the table. Right, and as I said, this is what you will be asked to do, right? More difficult stuff than this, then eventually applying it, but as I said, you will never be asked to do that proof that I did for the Laplace transform of C. But anyway, right, so example 1. F of t equals t to the power of 4. Right, so it can be worded in loads of different ways, right? But this is a way of saying find the Laplace transform. So I've been given a normal function, lowercase f and t, and it wants a capital F and S. So that means it wants the Laplace transform, right? Right, so all I'm going to do is get the answer. So I start with my original function. Oh, sorry, that should be a normal bracket, not a curly bracket. Right, and I want to find the Laplace transform of f of t. So the internal bracket should be normal brackets, and the bracket that the Laplace transforms on should be curly brackets. I'm not going to take marks off if you don't do that, right? So that's the Laplace transform of t to the power of 4, right? That's what I need to do. So the Laplace transform of f of t gives me capital F of s, which is what we're looking for, right? So that's just what happens, it's just terminology, right? So I go to my table of functions. So if I look at my function, it's t with a power on it. So let's have a look at my table, right? So where's the function looks like t, which is a power on it. Well, that's a number, so it's not that. That's just t. Oh, there we go. There's one that's t with a power on it. And the power I've got is 4, right? So I'm just going to write this at the side, so hopefully you can see it, right? So it tells me that if f of t is t to the power of n, then f of s is n factorial over s to the power of n plus 1. Right? So that's the one from the table. I'm just writing that so you can see it. So I don't have the power of n, I've got the power of 4. Right? So that's going to be 4 factorial over s to the power of 5. As I said, here we go, we're already getting s's and 5's next to each other, but hey, just got to try and make them look different if we can. Right, so 4 factorial, remember factorial means, that means 4 times 3 times 2 times 1. Right, and remember, you've got a factorial button in your calculator, which is just shift and then that button there. So I've got 4, which gives me 24. Or I could just work out 4 times 3 times 2 times 1 in my head, which is what I would probably do in an exam. That's your final answer. The Laplace transform of t to the power of 4 is just 24 over s to the power of 5. Hope we're all happy with that. Right. Example 2. Right. So right. So we're looking at this thing here. So I want to find the Laplace transform. Now, one of the key things from the table, and we spoke about it earlier, was that if you have a number in front of the function you're Laplace transforming, so a constant multiplying your function, that constant doesn't do anything. That's what that rule says, right? So that means that A is not going to be involved in the Laplace transform, and it's just going to multiply like that. Apologise for the noise in the background, there's a building site next to me. Anyway, right, so this Laplace transform, so again I go to my table. My table says if f of t and f of s, so it tells me if f of t is e to the power of kt, then the Laplace transform is 1 over s take away k, right? So my k, my function is 5. So that's going to be 8 times 1 over s take away 8. So that means that f of s, I could have made that f of s there, doesn't really matter, is 8 over s take away 5. So that's 5. Seemed determined to make it put as many 5s in these questions as possible, so that's 8 over s take away 5. Right, so that's 5, so that becomes 5, so it's 1 over s take away 5. Right, let's just do a last one, a last couple, and then I'll give you some questions to try. Right, so example 3. So I've got and if you want, you can try this one yourself, but I'm certainly going to go through it for you, right? So, the Laplace transform of t, right, so as I've said, that's a constant multiplying a function in t, so that constant just goes outside your Laplace transform. Again, that 3 is just a constant, so that goes outside the Laplace transform. Okay, I'm just going to write the Laplace transforms I'm going to use up here. So you go to your table, and right, well I want a Laplace transform involving t squared. So I've got one for t, but that's no use to me because I've got a different power. I've got a squared, so that means I need to use that tn one again. So the formula was Tn equals n factorial over s n plus 1, s to the power n plus 1. So that's what I'm going to have to use for this one here. And then that's an exponential, so I'm going to have to use s exponential 1, and that was e to the power of kt is 1 over s take away k. Right, so this time I'm going to have to use the two Laplace transforms. You don't need to write a wee table at the side, that's what you're looking at in the booklet. I'm just trying to make it as clear as possible. Right, so the Laplace transform of f of t becomes capital Fs. So, first one, the 4 stays as it is. Right, so t squared is going to be, so that's 2 factorial over s cubed. So remember, you add 1 to the power 2 plus 1. Right, take away 3. And that's 1 over, now that's 4, so that's going to be s take away negative 4, like that. Let's just have a little look and sort this out. So 2 factorial is 2. And if we subtract a negative, it becomes an addition. Just like that there. So that's going to give me 8 over s cubed, subtract 3 over s plus 4. So I hope you're getting the gist of this. The Laplace transform only happens to the actual function with the t in it. For example, the constant that's multiplying it stays out front and isn't involved in the Laplace transform. The only time that a number like that would be involved in the Laplace transform is if it was by itself. Right, and I'll do an example of that just now. Right, so let's do an example with sine or cosine and a constant, since we've not done that yet. So let's do so f of t is this function here, and I've just made it seem quite complicated, but it's not really. Right, so I want to find the Laplace transform of f of t. So that's a constant, multiplying, so that's just staying like this. It's 4 times the Laplace transform of sine 3t plus 6 multiplied by the Laplace transform of t cubed. Take away 4 times the Laplace transform of e to the power of t squared, sorry, e to the power of negative 2t. But the one thing we've got to watch is that's a constant. It's not involved in another. It's not got a variable in it, so we have to consider that as a function, right? So that's plus the Laplace transform of 9. Right? So the only time a constant or a number like that is involved inside the Laplace transform is if it's on its own, effectively. Right, so Laplace transform t. Right, so that's 4 times the Laplace transform of sine 3t. So I get my table out, right, and hopefully if we get the table out, so I want to do sine 3t. So that's going to be 3 over s squared plus 3 squared. Right. Right, the Laplace transform of t cubed, that's just your t to the power of n. Laplace transform here, so if you t to the power of n, so it's t cubed, so that's going to be 3 factorial over s to the power of 4. Right, so then it's an exponential, So if I look at my exponential, I've got 2 in here, so it's just going to be 1 over s take away 2. And lastly, the Laplace transform of 9. So 9 is just a constant, so it's the one we actually proved earlier on. That constant, the Laplace transform of a constant is just that number over s. So that's just going to be plus 9 over s. Right. So let's just simplify this down. So that's just going to become capital F of s. Again, I could have done that up here. Now, I just kept it going. You can keep it as LFT if you want all the way down. It doesn't make a difference. Or you can change it to F of S at the start. Makes no difference to me. Just do whatever you're comfortable with, right? So I'm going to simplify that to make that 9 and multiply those together. So that's 12 over s squared plus 9. Right. 3 factorial 6. So that's going to be 36 s to the power of 4. Right, that's just going to give you 4 over s take away 2, and that 9 take away s, or 9 over s just stays the same. And that's the Laplace transform of that difficult looking function. Done as much as you possibly can. Right, I don't think it's that tricky, but right, what I want you to do is there's not really any good questions in the book on this, right? I've got, let's see if I can find my worksheet somewhere. Okay, I don't really particularly like the questions on this in the book, but so what I would like you to try is these 4 questions here. So find the Laplace transform of each of these functions. Hopefully you can see them. That's a t and that's a negative t. So the first one is t cubed take away t squared plus 5t plus 2. Then negative 2 cos 6t plus 5 sin 6t. Then 3 is 3e to the power of t take away 4e to the power of 2t plus 2e to the power of negative 4t. Then the fourth one is 7t plus 6e to the power of t, take away 2e to the power of negative t, take away 10. So those 4 questions are there if you want to attempt them. And where are we at? Okay, and these are the answers here to those first 4 questions. There they are there. Now, these might be written in a slightly different format to the way that I've written my 4 answers, but what I'm going to do is I'm going to put the solutions to those up later on. At the start of the next lecture, I'll do that as revision. The next lecture will be on inverse Laplace transforms and first shift theorem. That's when it starts getting a little bit more difficult, but I feel like we've done quite a lot as an introduction to Laplace transforms today.